Delaware Tech, Chemistry 110, Stoichiometry of gases at non-STP conditions. So we've already talked about how to do gas stoichiometry when we're at STP conditions, that is, standard temperature and pressure of 0 degrees centigrade or 273.15 degrees Kelvin, and a pressure of 1 atmosphere in the U.S. We use a metric unit when we're working anywhere outside of the U.S. But we haven't talked about how to do gas stoichiometry at non-STP conditions, which is everything else. And remember, reactions happen in moles, so we must be dealing with moles. If we know the volume of a gas, we need to convert it to moles. And when it's at STP, that's a very easy conversion. We know that 1 mole of gas is equivalent to 22.4 liters. So it's a quick conversion from liters to moles or moles to liters. But at non-STP, you have to calculate it yourself, and we use the ideal gas law to do that. The ideal gas law is PV equals nRT, and you've seen this in various versions, but this is the easiest one to use if you're trying to solve for one of the various variables in this equation. This is the one condition version of ideal gas law, so it's only one set of P, V, N, and T. And if we want to solve for N and we know V, we have to also know P and T, and we can just look up the R value, and we can use that to solve for N directly, N directly. And we would do that with this equation shown in red, and you get that by merely taking your original equation and dividing both sides by RT. That gets rid of the R and the T on the right, leaving you only with the N by itself. So N equals PV over RT. So that's the way you're going to convert volume to moles when you're doing stoichiometry problems where it's not done at STP. In other words, where you can't use the shortcut. Now, if you're going the other way around, let's say you want to find out the volume of the gas you have, and you have the number of moles, then you can use a different version of this one condition ideal gas law. So we start with the same PV over nRT, and this time it's quite simple to rearrange. You just divide both sides by P. That gets rid of the P on the left, and that leaves us with this equation for V, assuming we know N, but we also have to know T and P, and we can of course look up R. So now we have ways of going from V to N, that's the first one, and from N to V, the second one, at non-STP. But if you're at non-STP, you still need to know the temperature and pressure. So let's look at some actual stoichiometry problems. In this first example, we're going to use the same formula, same chemical formula we used when we were looking at STP, but different conditions this time. So we have this reaction, 2 NaCl plus sulfuric acid produce 2 hydrogen chloride gas units plus a sodium sulfate. And the question says at 25 degrees C, so already you should be thinking you need to turn this into Kelvin, and 715 millimeters of mercury, okay, remember to use the right R value when you're using the ideal gas law, what volume of HCl gas in liters will be generated as 10.2 grams of NaCl reacts with sulfuric acid? Now this seems really difficult, but let's see, what are we actually being asked for, and what are we given? Well, the thing we are given is 10 grams of sodium chloride. And the thing we are being asked for is the volume of a gas. It's a different molecule than the one we're being given. So what do we have to do? We have grams of sodium chloride. When we know we have to turn grams into moles, because everything's done in moles in chemistry. Once we have moles of sodium chloride, we can turn that into moles of anything else. We want HCl, so we turn that into moles of HCl. So we already know how to go from grams of NaCl to moles of NaCl. We use the molar mass of NaCl to do that. And you'll have to determine what that is. And then we can go from moles of any substance to any other substance using the balanced equation coefficients. And then once we have the moles of HCl gas, we can turn it into liters, but now we have to do a separate equation, and that will be the ideal gas law. And I'll just write ideal gas here. Oops. Okay, so you can do the first two together in one set, but the third one you really should do it in a separate equation. So I'm going to clear these notes here, and let's look at the first part. We already know how to go from grams of NaCl to moles of NaCl using the molar mass of NaCl, and we know how to convert moles of NaCl to moles of HCl by using the balanced equation coefficients. Well, this one's easy. It's 2 to 2, so nothing will change. And we can calculate the moles of NaCl as a result. You'll notice the grams cancel the grams, the moles of this cancel the moles of the same thing, and we're left with the moles of HCl. So we're pretty close to the final answer. We can't use STP because it's not at STP. Otherwise, we could just take this number of moles and multiply it by 22.4 liters per mole, and we get our answer. But we're not there, so we have to use different conditions. And that means we need a temperature and pressure and the ideal gas law to solve it. So we start with the ideal gas law. We want a volume. That's what we're being asked for. Remember, look at your original map here of how you're going to do the problem. So we need the volume, and that means we need to plug in the moles, the number of moles. We have that. The R value, we can look that up. The T value is 25 degrees centigrade, but you have to add 273, like always, 273.15 degrees to make it in degrees Kelvin, and that will be 298.15 degrees Kelvin. So now we have our temperature, we have our pressure, we have our number of moles. We just need to calculate our volume, and we plug in the values. In this case, we will use the R value that corresponds to millimeters of mercury in the unit. That's 62.364 liter millimeter of mercury, or liter torr per degree mole. And you'll see I built in the calculation to calculate degrees Kelvin here. We could just replace that with 298.15 degrees Kelvin. And then you do your calculation, and we find our final answer is 4.5 liters of HCl. And you'll notice we rounded it to two significant figures. That's because our 25 degrees is only in 2 sig figs, and that will limit how many significant figures will be in the final answer. Let's look at another problem. This time, we are being asked for a mass, and we are given a volume. So it says, what is the mass of NaCl in grams needed to produce 340 milliliters of HCl gas at 1.5 atmospheres at 20.0 degrees centigrade in the following? Now, if you'd like, you can make a table on the right side of this page and write your pressure, your volume, your number, which is unknown, and your temperature down and have a little table. I'm going to do something a little bit simpler to take a little less space. I'm just going to circle certain items here. That is our volume of gas. 1.51 atmospheres is our pressure, and 20.0 degrees centigrade is our temperature, though it has to be converted into Kelvin. And we're being asked for the mass in grams, the number of grams of NaCl. And what we have to start with is a volume of HCl. So let's think about this. We have a volume of HCl in milliliters. We, of course, need to turn that into liters. And once we have liters of gas, we can use the ideal gas law to calculate the moles of HCl. So the bright red arrow here represents using the ideal gas law in a separate equation. And then once you get the moles of HCl, you can use the standard methods of stoichiometry calculations to go from moles of HCl to moles of NaCl. That, of course, would be done by using your balanced equation coefficients. And then once you have moles of NaCl, you can turn it into grams of NaCl using the molar mass of NaCl. So you're going to have to do some side calculations in this, and you're going to have to break it up into pieces, but let's take this a step at a time. So the first step would be to turn your volume into liters, and that we do a simple conversion. We just divide by 1,000, really, to go from 340 milliliters to 0.340 liters. I've kept the 0 in because it's 3 significant figures, so make sure you keep that there. So now we have our volume of gas, and this is actually our corrected volume, our volume in the right units. And our temperature needs to be converted to Kelvin. We're going to add 273.15, so that 273.15 will become 293.15 degrees Kelvin. And now we have our temperature, we have our pressure, we have our volume. They're all in the right units. We will now look up the right R value because we're going to need that for our gas equation. And we use the ideal gas law that's rearranged to solve for N. And in this case, we use the R value that has the correct units, the liter atmosphere per degree mole. Atmosphere because that is what atmospheres are in the problem, and it has liters. We're using the liters version, so we turned our volume into liters. So all of the component units, atmospheres, liters, degrees, Kelvin, and moles, should all be in your R value. And so it has to be the right units and corresponding to the right number. And then I've shown you the actual calculation to calculate 293.15 degrees Kelvin, and you end up calculating a certain number of moles of HCl, 0.02134 moles of HCl gas. So now this takes us to this step. And now we use normal stoichiometry methods. I'm going to erase these notes here. So our normal methods of stoichiometry would be to take our moles of HCl, turn that into moles of NaCl. So if you look up at the top here, we're now going to do these two steps to go from moles of HCl to moles of NaCl, and then moles of NaCl to grams of NaCl. We can do this all in one shot using the appropriate conversion factors. So if we start with the number of moles of HCl that we just calculated, multiply it by the first conversion factor, which is our balanced equation coefficients, to convert moles of HCl to moles of NaCl. And then the second conversion factor is merely the molar mass of NaCl, which you have to calculate yourself. And that will convert our moles of NaCl to grams of NaCl. And you'll notice it's already rounded to 3 significant digits, because our starting material was in 3 significant digits, as was our pressure and even our temperature. So our final answer here is 1.25 grams of NaCl, and we'll stop here.